Okay, so building the activity for trapezoid and parallelogram. And I'm going to turn off the axes. I really don't need them. And I'm going to use the polygon tool. So let's see if I start down here. And I'm not too worried about labeling it the same way as them, as long as I have things in the same positions. So this is the polygon that they have listed in the worksheet here. And my points are labeled differently, but it's the same one. So now we want to imagine making a copy of this thing and rotating it 180 degrees, so then it would be upside down like this guy over here, and then reattaching it. So I'm going to make another version next to this. And let's see, I'm also going to, it's going to get, oh, it's okay. We'll just go with a bunch of points. So I'm going to rebuild the same trapezoid. And then I'm going to build its inverse. So starting at this point H, come around to G. Let's see, then we have to go across 1, 2, 3, 4, 5 points. 1, 2, 3, 4, 5 points. And we go down and over. And so now I have a 180-degree reflection of it and attached to it. I want to play around with these in my notebook. Let's get the notebook out. All right, magic pen. Okay, so just a couple things to note about the relationship here. Are you getting these built okay, Kelly? How's it going, Kelly? You got it built?
I just need to do the other two that are together.
Okay. I'll give you a moment to do that. You got it close enough, Kelly?
I think so.
Okay, it doesn't need to be perfect. It just needs to be in the rough shape. Okay.
Do you want me to show you it?
No, you're okay. I'm just going to show you what I'm going to do with my sketch here.
Okay.
So I've got mine up on my whiteboard here. So just a few things about it. So my original trapezoid here has a base here of 5 units wide, and the top part is 2. And remember, height is measured vertically. So in this case, the height is 2 units. Now, if we compare that to the parallelogram we built by rotating this and sticking it back on, we now have across the bottom, my pen is not behaving, let me recenter it. Prior to misbehaving pen. Looks like we should be okay. So it now has a base of 7, and the top is also 7. Right? If it's a parallelogram, opposite sides have to be the same length because opposite sides are parallel. Here we also have a height of 2. And if you remember from our work in the last class for a parallelogram, the area is just the base times the height. So in this case, the area of the parallelogram is 7 times 2, or 14 square units. Now the question is, what's the relationship between the parallelogram and the trapezoid? Well, since I built the parallelogram out of 2 trapezoids, the parallelogram must be twice as big. So to find the area of the trapezoid, I should just be able to take the parallelogram area, 7 times 2, and cut it in half. So the area of my trapezoid should be 7 square units. Now some other things to double check. The 7 that I have here that made up the base, that came from taking 5 plus 2. The 5 was the base of the old trapezoid, and the 2 was the top of the old trapezoid because of that rotation we made. So if I break this down a little bit more.
It's because you flipped one over. That's why it's...
Exactly. Yeah, that's why. So for this particular trapezoid, to end up at the area, we ended up with a 5 plus a 2. We multiplied by the height, and we divided it by 2. And again, we had to divide by 2 here because we doubled that trapezoid to build the parallelogram. So what we're going to do is we're going to build another trapezoid, and then we're going to flip it, rotate it, excuse me, and stick it back on and see what happens. So let's make a new trapezoid and see if something similar happens. So here I'm just going to do it on doc paper this time. And so you could just sketch on a piece of paper, or if you happen to have some dot paper, that's cool too. So we're going to make a different parallelogram. So let's see, what should we build this time? Let's start up here, maybe with that point. And let's go down 3 over 1. So there's another point. And then we could go over 3 from that one. And for it to be a trapezoid, it has to have a pair of parallel sides. And usually I like to make the top and bottom parallel, but it doesn't matter. So then here, maybe I'll go over 3 and up 3 over here. So here's my trapezoid. So I started in the upper left. I went down 3 over 1 to here. And then I went over 3 units to there, and then over 3 up 3 to get the upper right corner, and now I have my other parallel side there. So I'm going to re-sketch that underneath, and I'm going to rotate and double it. So here's the original one underneath, so maybe I'll go right here. So down 3 over 1 puts me there. Over 3 puts me here. Over 3 up 3 puts me there. Now reversing this, if we double check, when I flip it, the top here is going to become the bottom, and it's going to have 1, 2, 3, 4, 5, 6, 7 units long. So from this point right here, I'm going to come out 1, 2, 3, 4, 5, 6, 7 units. Reversing the idea of from here, I went down 3 over 1. Here I want to go up 3 over 1. That'll take me to this point right here. Oops, I went the wrong direction, sorry. That would take me to this point right there. There we go. And then I should find that the remaining distance from this point to that one should be 1, 2, 3 units long. So just double check some measurements here. The original one had a bottom that was 3 units and a top that was 7. When I rotated it 180 degrees, it now has a bottom here that's 7 and a top that's 3. To go along with this one that had a bottom of 3 and a top of 7. So for the parallelogram, we're combining these guys. So now both the top and the bottom are 10 units. And we know that the area of a parallelogram is just base times the height. So in this case, this would be 10 times the height. And the height here is perpendicular to the top and bottom. That's 3 units. So then I get 10 times 3. So the parallelogram has an area of 30 squares. And what's the relationship between the area of the trapezoid and the parallelogram? Listen, the parallelogram is twice as big, right? Trapezoid is half the size. So if I want the area of the trapezoid here, then I'm going to take that 30, divide it by 2, and so I should be able to figure out that there's 15 squares. In my trapezoid. And we can chop it up like we did last week to try and figure that out. And so I want to break this apart again like I did last time. But before I do this, I want to cut it up and find the 15 a different way. But the flipping to a parallelogram actually gives me a formula for a trapezoid, which is pretty darn cool. So let's see, I want to copy the whole thing. just want to copy the background. All right, so I'm just going to mess with this one more time and convert the 15, then we'll pick it apart and we'll repeat this one more time. So it's here, 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 and there. So here's my figure. And I'm going to dissect this in the following way. I'm going to cut this part off here. And then in here, I can see that this figure is 3 by 3. So there's 9 squares in that part. This triangle over here, you'll note that it has a base of, let's see, 3 up here and a height of 3 right there. And the area of the triangle is 1/2 times the base times the height. Well, 3 times 3 is 9. Half of 9 is 4.5 or 4.5. And then this triangle on the right, the left, excuse me, if I dissect this triangle here, if you kind of look at it flipped, it has a base of 1 and a height of 3. So its area is 1/2 times its base times its height. Well, 1 times 3 is 3, and if I take half of that, I get 1.5. So if I put all these areas together, 9 plus 4.5 is 13.5, plus 1.5 gives me a total number of squares of 15 square units. So that's the dissection method we used before. And the dissection method is great, it works fantastic, but it's not going to lead us to a formula. All right, so 2 different ways we came up with. The area of this trapezoid is 15 square units. So I want to break apart that 15 again in terms of the trapezoid. So to do that, I have to identify, where did this 10 come again from? Well, let's see, the 10 came from the original base of 3 and flipping it to get the top down there, which is 7. So for my trapezoid here, I took the old base of 3, added the top, I multiplied that by the height, which was 3, and then I divided by 2. And if you double check, that's the same thing we did the first time. We took the old base plus the top, added those up, then multiplied by the height, and then cut it in half. So I think we might have a formula, and we're going to test that formula out. So I think that the area of the trapezoid can be found by taking the base, adding to that the top length. After you add those together, you can multiply by the height, and then divide by 2. I'll justify this formula in a different way in just a minute, but let's test it again. So to test it, I need you to make a new trapezoid that's different than the first one or the second one. And then I'm going to do the same thing. So let's see, to do that, I need a new page. And we could either do this on dot paper or in GeoGebra. Either way, ooh, not that GeoGebra. My other GeoGebra. The nice thing about doing it in GeoGebra is GeoGebra will calculate the area for you after. So I'm going to start a new sheet here. Don't need this one. Algebra, grid, no axes. All right, so make yourself a new trapezoid. And I'm going to make a new one, and we're going to test our formula. Ready, set, go. right, so I'm going to try this with my trapezoid. Let's see, I don't want that anymore. So all I have to do is measure. You know, often trapezoids are built so that the longer side is at the bottom, but like the exact last example, it doesn't have to be that way. So let's see, my bottom base. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 units long. My top base is 1, 2, 3, 4, 5. My height is 1, 2, 3, 4, 5. All right, so my formula says to take the bottom, add it to the top, put it in parentheses, and multiply by the height, and then cut all of that in half. So let's see, 13 and 5 is 18. 2 goes into 18 9 times. 9 times 5. My formula claims that the area is 45 square units. So I'm going to ask GeoGebra if that's true, and then Kelly, I'm going to ask you in just a minute about your trapezoid. So let's see here, GeoGebra has an area tool that's hidden behind the angle tool. So if I click the angle tool and then scroll down to area, and then I just point at my finger and click, GeoGebra says it's 45. Let's blow that out for everyone else. Let's see, options, font size, 24. Thank you, GeoGebra. So the area is just like my formula predicted. How you doing out there, Kelly? What are the dimensions of your trapezoid?
The top is 3, the height is 1, and the base is 5.
Okay, so let's see. Okay, so according to our formula, the area is going to be 5 plus 2, 10 times 1, divided by 2. So 5 and 3, so the total area should be 4 squares, according to our formula. Okay. Now I'm going to ask GeoGebra. Let's see if I can build this. Now mine might not be the exact same shape, but this is kind of cool. It turns out it doesn't matter that much. So let's see, your top base, okay, so you had a base of 5. So let's say I click here, oops, polygon tool, and then over 1, 2, 3, 4, 5, and then I go up 1, which could be here or there, I'm gonna go here, and then over 1, 2, 3. So here's a trapezoid that meets the description you gave me. And I could ask for the area, and GeoGebra says 4. And the cool thing is, it doesn't matter how I orient that, that's always gonna work. So what if instead I went here, and then I went up and over there, and then over 1, 2, 3, and then back down. So this would be an isosceles trapezoid. And its area is also 4. So it turns out there's a bunch of different trapezoids that each have the same area, as long, and all that matters is that they have the same base, same height, and same top.
The one on the right is the one that looks like mine.
The one on the right. So you made an isosceles trapezoid.
Yeah.
Yeah. So check it out. I'll make one more just for fun. That's like yours. Oops. Let's go and click here. Let's put it here. 1, 2, 3, 4, 5. And then what if I shot way over here? And then over 1, 2, 3. And then come back here. This is still a trapezoid, even though it looks pretty bizarre. Trapezoid has a pair, depending on the definitions, at least.
It kind of looks like a diamond.
Yeah, it's not a diamond, actually. In math, there's not really a definition for a diamond, but there is a kite.
Yeah, it looks like a really thin kite.
Yeah, this doesn't fit the kite definition either. But it does fit the trapezoid definition because line MN is parallel to line PO. But this thing does have a base of 5, a top of 10, and a height of 1. And if I ask GeoGebra what the area is, it's going to say, hey, that's an area of 4, too. Pretty amazing, isn't it? So here's another way to think about it. And I'm going to go back to my drawing board. Let's see. I think I will borrow this picture to do so. Page. Okay. So another way I could think about this is by cutting this ahead. With triangles on each side and a rectangle in the middle. Now the rectangle happens to be a square, that's a coincidence. Now the square rectangular part isn't the problem. That part's easy to calculate. Triangles aren't that bad either. So the next thing I want to do is imagine taking, let's say the base of this triangle is 2. If I cut that in half and I take this leftover chunk here and I cut it off, it will fit perfectly up top there. And then I do the same thing to this one. It's, let's see, 1, 2, 3, 4, 5, 6 units across. So if I come across 3 units and I slice, this triangle right here can be cut off and it will fit perfectly right up there. And if I do that, then what I've created is a rectangle instead of a parallelogram. And the area of this rectangle will be the same as the area of my trapezoid. Some things to check about this. By splitting these triangles in half and flipping their parts up or down, my claim is what I've done is I took my old base, which was, I believe, 13, and my top, which was 5, and I basically averaged them. So 5 and 13 is 18 divided by 2 is 9. So I've created instead a rectangle that has an average width of 9. And if we just double check here, I have 1, 2, 3, 5, 6, 7, 8, 9 for the width. The height is still the same as before. So this is an average width. Sometimes people call it the average base. And the height is still the same. That's 5. And so base times height still gives me an area of 45. So another way to think about the formula for the area of a trapezoid is to take the average of the top and the bottom and multiply that by the height. And that's just a variation of the formula we found earlier. We're just doing the divide by 2 at a different stage. But if you look, that has the same components as our other formula. Let's see, what was our other formula? Somewhere right there. Here's my top plus bottom over 2 times the height. So it's just a different way of organizing the arithmetic. Oops. And I just realized I forgot to invite Debbie. Let's invite her quick. So we had a couple different ways to work on the area of a trapezoid, which is pretty cool. Hi, Debbie. Sorry for not inviting you sooner.
That's all right.
There was nobody on campus today, so things were a little weird.
Oh, yeah, I can imagine. Sorry.
That's okay. Kelly and I have been chatting online for a little bit. So we just reviewed some of the things from last week, like the area of a rectangle, area of a parallelogram, and we just went through activity 4 in the workbook, which is area of a trapezoid. And
is that the first activity we're doing?
Yeah, and so I posted a note on our website that says, if I can find our website, that we are going to do activities 4, 7, 8, and 9.
Okay.
And 4 and 7 are related to sections 14.1 and 14.2 in the book.
Okay.
And 8 and 9 are related to sections 3 and 4. Which we're going to start taking a look at soon. I don't think we're going to get to those today, though. We still have to do some more work with the Pythagorean theorem and with circles.
Sounds good.
Okay. So let's see. Next thing we need to do. So the first part of this video has all of the activity 4 stuff that you need.
Okay.
Let's take a look at activity 7. And you do have the workbook, correct?
I do, yes.
All right. So I'm going to bring up my version of activity 7 here. There it is. Okay, so we're going to play around with right triangles. And there's a few different ways we can mess around with this. Activity 7 has us use graph paper, and it recommends centimeter graph paper. Most people don't have centimeter graph paper hanging around at home. Fortunately, if you search the internet for graph paper, there's a variety of websites that will give you graph paper. The one called Incompetech.com lets you design your own graph paper.
Okay.
And so I'm going to use that right now to design some centimeter graph paper to play with. And this one is pretty hands-on, so I'm going to have a hard time demonstrating this with the computer, but I will try. It requires scissors, which are hard to use on a screen. All right, so if I go to Incompetech's website, in their square paper section, I can just go to the regular squares section. And there I can choose just the regular row graph paper. And then what I'd like for them is they're verifying you want 8.5 by 11 inch paper. That's fine. The border's not a big deal. The line weight can be, so depending on your printer, a line weight of 0.5 could be too light or just okay. For most printers, I think 0.5 is pretty good. And then I'm going to switch the grid spacing from inch to centimeter. And I want to put a line every centimeter. So every 1 centimeter, I'll put a line. On my black and white printer, the light blue comes out too light, so I'm just going to switch that over to black. And then I download a PDF. And so let's call this plane 1 centimeter. And then I can bring it up, and I can decide if I think that'll look good. And so I can also paste this to our course website. So let's do that too. Let's see, did I already paste a graph paper link here somewhere? Online graph paper. Hexadecimal isometric equilateral. Okay, we're not ready for those. That's the next thing we're going to do after 3D stuff. Okay, so I'm going to post a new link here. Okay, so you could go to my link, or you could download your own graph paper. Okay, so 1 centimeter square graph paper. Okay, so now there's an announcement that has a link to the file I created, so anybody else could grab it, or you could make your own. And so the gist of this, and I'm just going to do a slightly different variation of it, is of this lab, is to cut out some squares, a 3 by 3, which is 9, a 4 by 4, a 5 by 5, 6 by 6, 7 by 7, 8 by 8, and so on. And then what we want to do is we want to try and put those together to see if we can make a right triangle out of it. And the way we're going to test to see if it's a right triangle, well, we should just be able to look at it and see. But sometimes it's close and hard to tell. But the Pythagorean theorem will always give us a sure way to test it out. So let's review the Pythagorean theorem. And then I'm going to give you another cutout activity to try. New page. Okay, Pythagorean theorem. Remember, so the Pythagorean theorem, remember, is related to right triangles. A kind of cool side note, it turns out there's a version of the Pythagorean theorem that works on any triangle. We're going to do the right triangle version. The non-right triangle version is a little crazy. All right, and so what it says is if you have a right triangle, and any orientation you want, the key is there's got to be a right angle there. The sides adjacent to the right angle are called your legs. So these guys here are my legs, and they're labeled A and B, and it doesn't matter which one is A and which one is B. And then the side opposite the right angle, that's the hypotenuse. And the hypotenuse is usually labeled C. And what the Pythagorean theorem says, that if you take A and B and you square their lengths and then add them up, that's always going to give you the square of the longest side.
I get it. Well, you don't have a class.
Teleclass, sorry. So the gist of this situation is we're going to see which of these squared lengths will build a right triangle. And we'll see that some of them do and some of them don't. Other things we'll take a look at here, is the resulting triangle obtuse like this one here, or is it acute, or is it right? And what we should find is that if it's a right triangle, that the two smaller squares add up to be the big square. And so that is our experiment there. Okay. So the next thing I need you to do is get a couple pieces of paper probably. You could probably do it with one piece, and some scissors. And I'm going to attempt to do it with my whiteboard here. I think I can pull this off. And what you want to do with your piece of paper is cut out 4 identical right triangles. So design an original right triangle. And the easy way to do it, but it could waste more paper, is to stack 4 pieces of paper together and cut. And then you get 4 identical triangles. Otherwise, you have to trace it and cut it. But somehow come up with 4 identical triangles made out of paper. And what we're going to do is we're going to play around with those 4 paper triangles and see if we can justify the Pythagorean theorem. So paper and scissors are important here. So I'm going to try and do mine digitally. So we want to try and sketch or cut and sketch, however you can do it, 4 triangles. It's easier to make them identical if you use graph paper, but as close as possible. They don't have to be perfect.
I just folded a piece of paper in fourths and then cut one out.
Okay. Oh, that's a good idea. Beautiful. Okay. So the next thing we need to happen is we need to the best of our ability, build squares coming off each side of one of our triangles. So for example, I'd focus on this one right here, and maybe I'll change its color. And I want to, whatever length, so if I call this short side A, I want to build a square that's A by A off of that. And then if I call this bottom side, the medium size side B, I want to make a square of length B off of that, and so on. So here's where it's going to start getting interesting. Let's see, ungroup this, give that a shot. Probably not going to work. Okay, so I'm going to have to whip out a ruler here to try and measure this sucker. It's about 6.5 centimeters. And so what you're going to end up doing is cutting that square out of paper. So I'm doing my best to build mine here. Let's see. So we want to build, so this guy right here I might call like b squared. This side here is b. All right, so let's see if I can reproduce the next one. All right. The hard part for me digitally is going to draw c squared. Oops. Let's make you a different color, black. Okay. All right, I'm almost there. So again, your goal is to get 4 triangles of the same size, a square that's about the square of your short side, a square that's about the square of your medium side, and a square that's about the square of your long side. To the best of your cutting abilities. All right, so let's see if I can pull off my c squared. Slightly off my screen. It's way easier to do by hand. Should go about right there. Okay, that's about as close as I can get with these tools. All right, so let's see. I'm running out of colors. That. Then colorize it yellow, orange. No, green. Okay, that'll work. All right, so when I put these guys together, they are the sides that meet are the origins of my right triangle. Do the best job of building this, but it's close. Okay, there we go. So, so what I want you to do on paper is just imagine a couple of things here. If I take this guy here, flip it around, and I reposition it up here, and I grab this one, and I reposition it down here, and then I take this guy here, rotate it, Just rotate a little too much. And I stick this down here. These shapes, pull this guy out, form a square. And so double check, what are the measurements of this square? Well, the measurements of this square are A plus B over here and A plus B over there. Agreed? And you should be able to do a similar thing with your 2 little squares and your 4 triangles. Are you able to put them together in a configuration like that? So we're ignoring the big square for a minute. We've got our 2 little squares and our 4 congruent right triangles. Now I'm going to put these together in a slightly different way and see what happens. Oops. I'm going to take these triangles and I'm going to move them to play with the other. So I'm going to rotate this around. And I'm going to stick that up here. So I'm trying to get it to line up. And that's going to be easier for you and harder for me. Mine does not want to work quite right. Oops. Almost. So if all my drawings were lined up properly, I should be able to stick my triangles around the outside of my big rectangle. And again, my lines weren't drawn perfectly. Maybe I should have done this in GeoGebra. So that the 4 triangles should fit around that big square and make another bigger square.
Mm-hmm.
So you have to reposition yours to make that happen. So I've got this new square here. What are the dimensions of my new square? Well, similar to before, this is A plus B by A plus B. So I've just made 2 squares that are exactly the same size in 2 different ways. I have this second one here made with the big square in the middle, and I have this one here with the 2 smaller squares on the corners. So what do these 2 figures have in common? So I'm going to borrow these guys and bring them to my other screen. Let's take them to a whole new screen. So just some things to consider here. Both of these bigger squares have exactly the same area because they're both A plus B by A plus B. They also have something else in common. What else do they have in common?
Well, the perimeters would be the same.
The perimeters would be the same. Okay, what else do they have in common? Something else in common. What do they have in common inside?
Triangles.
They both have these exact 4 same triangles in common inside. So this triangle here has exactly the same area as this triangle here. Oops, I missed the letter up top. And if we remove these red-yellow triangles, then the remaining pieces have to be equal also. So that is, if we remove these triangles, I highlighted in yellow from the upper right, and if I remove these from the one on the lower left, what's going to be left in each case is this area here and this area here compared to this area over here. So if we start with equal areas and then we remove 4 equal parts, the remaining areas have to be the same. So this is a picture proof of the Pythagorean theorem. What these two figures show us is that in the little picture, the a squared combined with the b squared have to have the same area as the c squared. So this is one way to justify why the heck the Pythagorean theorem works. So I'm going to show you one more way, and then we're going to have to take a, let's see, do I have time to show one more way? We're running out of time. I could either show one more reason why the Pythagorean theorem works, or we could take a quick look at pi. Any requests out there, pi or the Pythagorean theorem again?
Well, I understand the Pythagorean theorem. My question is on the activity though.
Yeah.
When we get down to where it has just 169, we just play with the triangles until we find something that can match up with it?
You want to try and build a triangle with 2 other sides.
Okay.
So the 169 is the 13. So we're saying make a hypotenuse of 13.
Right.
Can you use any of the other lengths to make 2 legs to form a triangle?
Okay. So we just take the squares that we have cut out and
Yeah.
kind of lay them together like this picture is in our activity book.
Correct. Yeah. You want to lay them together like that to make a triangle, and then what we want to do is with this chart here, check to see if we end up with a match for the Pythagorean theorem or not.
Okay. So everybody's answers won't be identical.
Correct. Yes. You're right. They won't necessarily be identical, depending on which 2 lengths or which 2 squares they tried to bundle with that hypotenuse.
Okay. And then for the second one, when we move over to the next page, some of our answers are going to be identical because we're going to use the same matchups. So like the sum of the areas of the 2 smaller squares was 45, and so it will also be 45 in the next one.
Correct.
Okay.
Yeah. So play around with that, and then we'll debrief on that in the next class.
Sounds good.
Okay. So I'm going to take a quick look at pi. We'll set the Pythagorean theorem aside for now until next class. So pi, a lot of people know to be approximately 3.14. One wild thing about pi, which other numbers have this same wild property, I'm going to ask a website for pi's decimal places. Let's go to Wolfram Alpha. Ask about pi. And I've always liked playing at Wolfram Alpha because they have this button here called More Digits. And I can keep clicking it. And eventually it tells me to knock it off. It's not going to give me any more. But one thing about pi is, unlike a fraction like 1/7 or 1/3, pi doesn't repeat a regular pattern that I can rubber stamp over and over again. And try as people might, for ages now, no one has found a pattern. Now, there are some wild things we can do with computers and pi and different number systems, but that's another story. So pi is called an irrational number because it can't be written as the ratio of two whole numbers. Oops, wrong button. So that's another thing to note about pi. Pi is irrational, which means it can't be written as the ratio of two whole numbers. So where did pi come from? Well, a long time ago, people discovered that on a circle, if they compared as a ratio the circumference to the diameter, they always got about the same number. And later, we realized that number is what we know today as pi. Now, first they knew it was about 3. And then people figured out it was about 3 1/10. And then they figured out it was 3 1400ths. Another popular approximation of pi, 3 is very popular. That's what I use when I don't have a calculator around. If my calculator doesn't have a pi button, I'll often use 3.14. 3 1/7 is another popular one, which could also be written as 3 times 7 is 21, 22 sevenths. Okay, so there's some pieces of pi. So historically, we discovered pi when people realized that the ratio, if we took the circumference of a circle, we measured it well, we took the diameter, we measured it well, and we did our division well, we would get about pi each time. Now, did we get exactly pi? Well, there's error in measurement, and division is very challenging. But we've known about this for thousands of years, which is kind of cool. All right, so I'm going to draw a circle here on my screen. And I am going to dissect it. So here's my circle right there, let's say. And then what I'm going to do is I'm going to chop my circle up by drawing a bunch of diameters. And maybe, so we could go 8s. We could take those 8s and cut those in half and get 16ths if we wanted to. And then after that, it's going to get very messy. So imagine this was a pizza that we cut up. We want to play with a new arrangement of that pizza. But one thing we could do is we could take those pieces out and lay it down a different way. And so it's possible to rearrange the slices in a manner like this, where we alternate up, down, up, down, up, down. So if I have 16 slices, that means I can make 8 facing down and 8 facing up. I'm going to do my best to sketch that. 1, 2, 3, 4, 5, 6, 7, 8. And then down below, I'll similarly have 1, 2, 3, 4, 5, 6, 7. Second, zero. There. Let's try that last time. That's 1, 2, 3, 4, 5, 6, 7. So it's going to look something like this. Now, the more pieces you make and reposition it like this, the more it's going to look like a special geometric figure that we analyzed last week. What figure is this starting to resemble? A little messy.
Like the whole outside that you're talking about?
Yeah, the shape I've just made by rearranging these pieces. What does that kind of look like? What polygon?
Parallelogram.
That's a parallelogram. So I'm just going to double check its parallelogramness. Okay, some things to note about this parallelogram. The more slices I make, the flatter the top will get. Right now, it's a bunch of little arches. But what I've done is I've split. Half of the circumference is now across the top, and half of the circumference is across the bottom. What is the height of my parallelogram, do you think, here compared to the original circle? Is there any relationship between the height of my parallelogram and the original circle?
What the half circle would be?
The radius.
Yeah, right. Yeah, so the height of my parallelogram is one of the radii of these slices of pizza. So that's the radius. Okay, so let's see. So I have a height that's equal to the radius. Now, again, this isn't a perfect parallelogram, but the more slices, little slices I make, the closer it gets to a parallelogram. And so the limiting process of this, I'm going to get an area. Now, anybody remember the area formula for parallelogram?
Base times height.
Base times height, yeah. And my base here is 1/2 of the circumference. And my height here is the radius. Okay, let's see. What can we do with that? That's getting kind of weird. Back up a page here. Okay, circumference over diameter is pi. Usually people remember that relationship as their circumference is pi times the diameter. Now, I remember seeing the red way, and I was totally blown away. It's like changed my worldview. Any circle, no matter how big or how small, circumference divided by diameter is always pi. That just blew my mind as a kid. Okay, so circumference is pi times the diameter. So let's take that fact and throw it into this thing over here. So that means I can replace the circumference here with pi times the diameter in my area formula. Okay, so I could also say the area is, there's the 1/2. Circumference is really pi times the diameter. And then we've got, so that, replace that. And we've got r hanging out there. We're venturing a little into algebra. Okay, but there's too many letters here. Pi, d, r. Anybody know a relationship between the diameter and the radius?
Diameter is twice as big.
Yeah, diameter is twice as big. So I could tweak this yet again. Let's use a new color. So this is 1/2 times pi. Diameter, oops, what was that? The diameter could be rewritten as twice the radius. And then I've got this other radius hanging out there too. Now, let's see, can we clean this up a little bit? 1/2 times 2 is 1, right? So that can go away. And instead of writing r times r, I could instead write
R squared.
r squared, and this leads to the popular representation of a circle's area, which is pi times the radius squared.
That makes sense.
Isn't that cute? All from a pizza pie. And a parallelogram. Okay, so that's it for now. A little fun with circles and parallelograms and pi. So what we need to do is play around with that Activity 7 worksheet on your own, and then we'll debrief on that on, let's see, today is Monday, on Wednesday. Debbie, the first half of this recording went over Activity 4.
Okay.
Take a peek at that. I don't think you'll have much problem with Activity 4. It's pretty straightforward. It's a one-pager. And then that is most of the material in sections 1 and 2 of Chapter 14. There's a few other little things we'll have to clean up on Wednesday. And then once we do that, we'll be ready to play with three-dimensional geometry.
Okay.
All right. And I'm going to hold off on posting the 3D geometry homework because we still have enough to do with the 2D stuff here.
Sounds good.
But the activities 8 and 9, those are 3D geometry. And those will involve some some paper cutting also, possibly tape and glue. So let's see, I pointed this out earlier in the recording. Under Tools for Success, oops, wrong button. There's an Activity Masters, and those are the cutouts in the back of your book. And so, for example, we will need some of the polyhedral nets to do Activity 7. Oh, no, let's see, 4, 7, 8. Activity 8, excuse me.
Okay.
They're either on the back of the book or you can print them from our website.
So they're like in the papers and we have to cut them out? Oh, I see them.
Yeah, see them in the papers?
Yeah.
Yeah, not in the colorful dotted line cutout ones. They're still attached inside the book.
Okay.
But they're also available in the website too, which is nice because I'm not the best cutter, and so it's good to have a backup to cut out.
Right.
And so we're taking a look at what is a polyhedral net and how does that work with 2D versus 3D connection. And so that's what we're going to play around with once we're done with the Pythagorean theorem and a couple other area problems. All right, that's it for now. Any questions?
I don't think so.
When's our next test?
The final exam.
Okay.
I'd rather not give another test. And the final exam will be part take home.
Okay.
So I'll have a sample of that out soon.
Okay.
All right. Okay, that's it for today. I'll see you all on Wednesday. Thanks.
Have a nice Tuesday.
Okay, too. Bye-bye.